Hello everyone, welcome to my channel Coding Together. My name is Vikas Oja. Today we will see another algorithm that is called Kahn's algorithm for topological sorting. So what is topological sorting? So topological sorting in directed acyclic graph, that is DAG, directed acyclic graph, is the linear ordering of the vertices such that for every edge uv, right, for any edge starting with vertex u and ending on vertex v, u comes before v in the ordering. So let's see the topological sorting for this graph. So this is the topological sorting 542310. If you see for any edge, so let's see this edge starting from the node 5 and ending on node 2. 5 comes before the 2, right? So this is the linear ordering of all the vertices for this graph, and for any edge the vertex u comes before v in the ordering. So for example, for the edge that is starting from 4 and ending at 0, 4 comes before 0, right? So for any edge u will come before v. So that linear ordering is called the topological sorting. So let's see how we can use Kahn's algorithm for this topological sorting. So first of all, we are given with the adjacency list for this particular graph. So on the left side we have this node, right, and on the right side is the neighbors of that particular node or the child of that particular node. So from 0, right, there is no edge going out of the 0, so there is no neighbor or there is no child nodes of the 0. From 1 has also no child nodes. From 2 there is an edge from 2 to 3. So we have captured that in the adjacency list with 2 as a starting node and 3 as an ending node. Again, from 3 we have a node from 3 to 1. From 4 we have a node from 4 to 1 and 4 to 0. So for the node 4 we have two neighbors, that is 0 and 1, right? And for 5 we have two neighbor nodes, that is 0 and 2, because there are two edges from going out from the vertex 5. That is, one is this, that is coming out from 5 and going to 2, and one edge coming from 5 and going to 0. So this is the adjacency list that we already have. Now what we will maintain the in degree for each vertex, right? So what do we mean by in degree? In degree means number of edges pointing towards that vertex or coming into that vertex. So suppose if we see the node 0, the in degree will be 2, because there are two edges that are coming into the vertex 0, one from 4 and one from 5. Similarly, for 1, number of edges coming into 1 are 2, so the in degree is 2, one from 3 and one from 4. Similarly, for 2, the in degree is 1. For 3, in degree is 1. For 4, in degree is 0. For 5, in degree is 0. For 4 and 5, in degree is 0, because there are no edges coming into into those vertex. Now we will also maintain a data structure, that is Q, because Kahn's algorithm follows BFS, breadth first search, for the graph traversal, right? So first we will take all the nodes, all the vertices with the in degree 0. So we have 4 and 5 as in degree 0, so we'll put 4 and 5 in the queue. Right, now we will poll the first element of the queue, that is 4, right, and we will print the 4, right. So we will maintain an output. So we'll first print 4. Now for 4 we'll see the adjacency list. So the corresponding adjacent nodes for the node for the vertex 4 is 0, 1. So for 4 the adjacent vertices are 0, 1, or you can say neighbors are 0, 1. So for 0 we'll reduce the in degree by 1, that is now from 2 it will become 1, and for 1 as well we'll reduce the in degree to 1, right. Now we will extract 5 from the queue and we'll put it into the output, right. And for 5 the neighbors are 0, 2. So we'll reduce the in degree of 0 once again. So in degree will reduce from 1 to 0. So as the in degree has become 0, for 0 we'll add 0 in the queue, right. Now for 2 the in degree is 1, so we'll reduce it to 0, and as the in degree has reduced to 0 we'll add 2 in the queue, right. Now all the neighbors are done for 5, so we'll poll from the queue 0, and for 0 in the adjacency list we don't have any neighbors, so we'll do nothing and we'll print it into the output. Now for 2, now we'll poll 2. So for 2 in the adjacency list, right, we have the neighbor as 3, right. So for 2 we will print and we'll work on 3. So for 3 we'll reduce the in degree to 0, because in degree is 1 for 3, so we'll reduce it by 1 and it becomes 0, and as soon as it becomes 0, so we'll add into the queue. So we'll add 3 into the queue, right. Now again we'll fetch 3, or we'll poll 3 from the queue. So for as soon as we poll 3 from the queue we'll print it or add into the output. Now for 3 the adjacency is 1, right, the adjacent vertices are 1. So for 1 the in degree is 1, so we'll reduce it to 0. So as the in degree has become 0 we'll add it into the queue, right. Now we'll poll 1 from the queue, and for 1 there is no adjacent vertices or neighbors, so we'll stop and we'll add 1 into the output. Now this is our topological sorting of the vertices, or the linear ordering of the vertices, in such a way that for any edge u comes before v. So this is our topological sorting, that is 4, 5, 0, 2, 3, 1. So we can verify that for any edge u will come before v. So for example, let's verify this 5, 2. So as the edge is starting from 5 and ending on 2, the 5 should come before 2. So yes, 5 is coming before 2. For 4, 0, 4 is coming before 0. For 3, 1, 3 is coming before 1. For 2, 3, 2 is coming before 3. And similarly for 5, 0, 5 is coming before 0. So for all the edges, vertex u is coming before vertex v. There can be multiple topological sortings of the vertices. First, like if you can see in this, for this example we have 1, 4, 5, 0, 2, 3, 1, and the other is 5, 4, 2, 3, 1, 0. So both are correct. So now let's see the code for this algorithm. So we have already created the graph in the form of adjacency list, right. in the adjacency list, and I've already explained how to create the adjacency list for a graph in the DFS and BFS video lectures. So I'll paste the link of these two traversal or these two videos in the description link of this video, so you can check that out to know how we create the adjacency list for a graph. Now we have created a in degree array of size n, where n denotes the number of vertices. So we are having one for loop starting from I equal to 0 until the number of vertices, and for each I mean for each node, will go into the adjacency list, and corresponding to the each node, right, will first find the neighbor nodes and increment the in degree for all those nodes. So right, so suppose for 4 will increment the in degree for 0 and 1, because for 0 and 1 there will be a edge coming from 4. Now we will maintain a queue, right, because as we know, for the BFS we use queue. Now we will in this for loop we'll first check for whichever the node the in degree is 0, right. So for this example, at the start the in degree for vertex 4 and vertex 5 was 0, so we will add in the queue all the vertex for those in degree is 0. So we'll start our BFS, right. So we'll iterate in the queue till it's not empty. So we'll pull the first element from the queue, right, and we'll print it, right, and after that we'll check the adjacent vertex for that node, right. So we'll check the adjacency list for that particular node, and we'll iterate for each neighbor for that node, and will decrement the in degree for that node, and as soon as the in degree becomes 0, we'll add it into the queue. So this is the code part for it. So let's see the time complexity and space complexity. So for time complexity, as this is a BFS, breadth first search of graph, so the time complexity will be big O of v plus c. This has been also explained in the video breadth first search traversal. So I'll paste the link of this video. And for the space complexity, so complexity will be big O of v, because in the worst case the queue can hold might have to hold all the vertices in the worst case. So the worst case complexity of the space complexity of this algorithm will be big O of v. So I hope you like this video, and if you like this video, please share and subscribe. This will keep me motivated to bring more such concepts and algorithms. Thanks for watching. Bye.